Sorry, I forgot to unmute myself while I was trying to make this go full screen. There, you should be seeing my full screen now, okay? Good. You can hear me and see me. Okay, so I'm Richard Milton, and Flora Roumpani is going to take the second half of this presentation. We're going to talk about the Quant2 model, which is Professor Mike Batty's urban model. But Quant is unusual in it being a web-based model. Now, I always use this slide to explain what Quant does. We've got 8,436 zones in the model. So it's a bigger model than most models are. And that's to counter the edge effects. So there's no edge to our model. It's a completely seamless model of England, Scotland, and Wales. And we've got 3 modes. So what you see on the graph here, on the maps here, you see the 3 different modes. Now, each one of those little blue arrows represents an average flow direction. So it's based on the census travel to work data. So all 20 million people going to work. And each arrow is a flow from the origin zone in the average direction of all the commuter flow from that zone. So when you look at the difference between the rail, the bus, and the road, you can see spatially there's quite a marked difference. But that's the base model that we've got. Now, for the original AI UK conference, we proposed a demonstrator, and this is called Quantscape. Now, this was to do 2 things. We wanted to get humans to be able to generate scenarios. So on a 55-inch touch table, we were going to run a version of Quant with, it's an exercise in human-computer interaction in the creation of scenarios. So we made the web interface that's currently quite difficult to use more easy to use for people. And so what we wanted to do was generate human-created scenarios. But we also wanted to pose the question, which is better and where is the cutoff? Do you want perfect information or is interactivity better? Because the problem with most urban models is that they take several hours to run. Now, obviously, in a web-based interface or in a Quantscape-based interface, that's not acceptable. So we have to use imperfect data. So we use approximations. So we pose that question, you know, how good a design can you create when you've got imperfect information? So at some point, hopefully, we'll be able to run that experiment as soon as we've released the table from its quarantine in the British Library. Now, as I said a moment ago, Quant is unusual in being web-based, but this also gives us some advantages. So this is the diagram of the overview of how Quant works. What I'm going to focus on is the web services box, because the rest of it just runs the website. It's the web services that are interesting because the web services are exposed to the outside world. And that means that the Quant web view that you normally see, you know, on the standard Quant website, it's just a client of the underlying infrastructure. But we can put other clients onto that, whether that be a 3D view of the Olympic Park that we see here, that was Flora's example in City Engine, or even the Quantscape example. Quantscape is just another client to that. I say immediate because obviously, you know, these clients have got to run immediately. There's no point having something on the web where you click on a button and you have to wait 2 hours for the model to tell you what the result is. And that has an impact in what we're looking at are approximate methods for, you know, approximating what would take 2 hours or more to run. Now, I've mentioned that the Quant model here, it takes 427 million floating point values to actually run its model. It's quite computationally significant. At the moment, we're running it GPU optimized. On the desktops, we've got a 10 teraflop GPU, but I've also tried it on a V100 100 teraflop GPU. That was until I used all of the Turing's $1,000 of Azure credits. The problem really comes from the networks, and I'll talk about more on this later, but we've got all pairs shortest paths algorithms being run on 8 million node networks. That is really the issue with the compute. Now, this big scary diagram shows all the inputs and outputs to the model. I'm not going to focus on this too much, but what I'm going to do is I'm going to say that this talk is really about that box at the bottom. How do you optimize a scenario? Because what we had at the starting point was we had the ability to create and run scenarios. So the red circle shows you the 2 types of scenarios that we can run. We can either run employment changes, So that would be like a Heathrow Airport example where you put new employment in. Or we can run network changes, which would be like an HS2 example where you've built a huge complicated rail network. The problem here is that if we do a network change, we then have to go back to the original network graphs. So if we've changed a road, we have to change that on the network graph, rerun the shortest paths, which for the road takes 2 hours. For the bus, it takes about 40 minutes. And for the rail, it can do about 2.5 minutes. But that's still too long for it to be really interactive. So that's what most of this presentation is about, how we actually run this interactively with the quant model. Now, this is an example of a scenario. So this is the Heathrow new runway scenario. So X marks the spot right in the middle of the screen where Heathrow is. The data for this is taken from the official government data for Heathrow. What's noticeable about this is you see where the green belt is and you see where the airport is. All of the new housing that's going to be required, this model is predicting that it's all going to be pushed into central London, where the current housing density is greatest. So that's quite a significant result. So that's an example of an employment scenario that we could do. I wanted to show a network change scenario as well. So this is the East-West Rail. Well, part of it is still proposed, but part of it's been built and part of it is currently being built. Now, this visualization shows the numbers of road kilometers driven. So what happens is we take the government, the map for where the new rail links are going to be, and we digitize that. We run a baseline model with no changes, and then we run a scenario model with the new network changes. And what we do is we difference one from the other. So what happens where you build a new fast rail link is that it attracts people who would normally have gone by car. The rail link is now attractive because it's a lower cost. And so people get attracted from road onto rail. And so when we difference the baseline and the scenario, what we find is that a lot of people have switched from their cars onto the rail. What we do then is we look at the trips that they were taking by the cars, we work out how many kilometers they would have driven, and that's what's plotted on this map. So this is basically a carbon scenario. So in the middle of the map, with a pattern that you wouldn't ordinarily, guess at from where that rail line is. It's not just following the rail line, it's following the commuter patterns. What we see is, what our carbon budget is going to be. And, building a rail line is good in terms of carbon. Putting jobs in tends to be bad in terms of carbon. I also wanted to show this because it shows the huge geographic area that's actually affected by an intervention like this. And if I move on to the next one, we're showing the same thing again. This is high-speed 2 rail example. So this is high-speed 2 phase 1 and 2. And you can see the effect that that's having in the Leeds areas and the Manchester areas. Now, because people know that we've been doing these examples and we've been doing HS2, people keep asking me, do you think it's a good idea to build HS2? And my answer is, I'm a computer scientist. Why are you asking me? But when you look at this, it shows something very important. If you see phase 1, which is London to Birmingham, there's no real benefit from that. But then when you see phase 2, which is Birmingham to Leeds and Birmingham to Manchester, you can see the difference in the carbon where it's taking people off of the roads. The reason for that is because it's basically going from Old Oak Common straight to Birmingham. There are no stops. If there are no stops, no one can get on and off. Therefore, you generate no benefit. But what this shows from an AI machine learning point of view, you've got to build phase 1 before you can gain the benefits of building phase 2. So in our search through model space, what we've actually got to do is to sometimes take a step backwards in order to take a big step forwards. And that's what's shown on this graph here. If you look down in the bottom right-hand corner, you can see HS2 phase 1 and 2. Now, left to right on this graph, as you move towards the right, that's where the larger network links, more network links are being added, bigger transport plan, more cost. So as you move to the right, cost increases. So HS2 phase 1 and 2 is 100 billion. It's expensive. Now in that cluster, just below the line, on the left, you can see HS2 phase 1, but that's clustered with Crossrail and East-West Rail as well. Now, below the 0 line, that's good in terms of carbon, so that's taking people off the road and putting them onto the rail. You can see Gatwick and Heathrow. We proposed a Gatwick scenario that's similar to Heathrow one, but you can see Heathrow and Gatwick, they add jobs, they don't add infrastructure. So all they're doing is adding a lot of people who are possibly going to drive to work. So you can only ever add carbon by adding jobs. So what you actually need is the two combined together. You need network infrastructure to go with increased jobs. So this is really the AI slide part of this. So these two maps show the two parts of the quant. So you've got on the left, you've got the job scenarios, and on the right, you've got the rail scenarios. Now, the jobs, the way I looked at it, it's more like a game playing AI, because what the map on the left is showing us is all 8,400 zones. And what I do is I increase the jobs in a zone by 10%, and then I look at the impacts. And so what you're seeing here is a rank of the impacts. So the red is showing you where it's suggesting is the first good place to put some increased jobs. Now, that's just the first step in the game. If you want to do the next step, then there's 8,400 possibilities of putting one intervention in, 8,400 squared of putting two interventions, cubed 3 interventions. So by the time you're looking at, for an example, the Heathrow scenario, put in 22 different job interventions. That would be 8,400 to the power of 22 if you wanted to check every single possible combination. So it's got a very big branching factor. Luckily, though, you can actually narrow the search. So rather than a sort of min-max type search, the Monte Carlo search idea is much more the way to do it. Now, the rail scenario, the rail is different. One of the things that this work has given us is the ability to compare scenarios that we didn't do before. And that comes through the evaluator that we use. Now, with the rail, what we do is we increase the speed of all the rail links, all of the rail links by 10%. So we give the system a big kick and see how it reacts. Then based on how it reacts, we then prune from that position. So what we do is we prune to the point where we're minimizing the costs while maximizing the impacts. But what's important here is the evaluator that you use has a big effect on the design that you end up with at the end. So here we're doing carbon, but we could be looking at mean trip lengths, we could be looking at total time saved, we could be looking at geographic effects. Now, the problem we're currently having is that when we compare the machine-generated scenarios to the human-generated scenarios, the machine-generated ones are creating 10 times the impact than the human ones, but at significant cost. The problem is, if you look at that rail map, it's generated small changes all over the map, which is unrealistic. The idea is, can we take the amount of money that's been used for HS2 and instead of doing one big intervention, make lots of small changes to the system, and through that generate more impact, but at reduced cost. And that's what the AI is currently being used to try to do. So it's all down to the evaluator that you use and how you use that evaluator, and you work out your costs in terms of real world scenarios rather than just artificial scenarios. So what I'm going to do now is I'm going to hand over to Flora. And what I'm going to ask is, how do we evaluate small scale models with a regional scale model? And how do we look at those effects in terms of, the real world that we have to live in and not just the model world? The mapping from one to the other is quite complicated. Okay, Flora, over to you.
Thank you, Richard. Right, so yes, so as Richard showed before, Quant is a very large regional model that calculates employment changes, population, and network changes and predicts the effects of these changes. However, it's quite interesting to understand that when we do these regional changes, and especially in the case of the UK, regional changes affect the local scale, and local scale affects the regional scale. So the answer, in a way, as to how do we evaluate the small local changes that come from a very big regional model is to develop a two-tier system that allows the communication between a big regional model and a lower tier urban planning model. So the vision in this work is to use this external model of Quant, which is very powerful and calculates land use demand on a regional level, and use it to evaluate a small area plan, such as a neighborhood or a new development. So in this diagram, Quant lies on the right-hand side in the science, models and analysis outputs and planning indicators. And what we do here is that we feed Quant into a visualization that is interactive, and it consists of lower tier planning models. Then we produce this modeling based scenarios here at the end. And what we need for that is the development at the center of this information hub, which allows the implementation of the existing model of Quant with this lower tier inputs all in one system. And as Richard showed before in his main diagram, it also allows this multiple visualizations in one system. So let's see this example, for example. So this is an external model. This was developed by Joel Durdern, and it's an external model of South Yorkshire. And we can see that how this feeds in to different types of visualization, whether these are like bars or internal lower tier zone ones. So the aim, in a sense, is to be able to explore and create digital tools that visualize a number of planning parameters or urban parameters, which can be manipulated within this geospatial environment and allowed to quickly understand the implication of different what-if urban planning scenarios. And that's what we're doing with Quantscape as well. So the way that we've achieved this through Quant is it's very simple. So Quant calculates population from employment. We get this population projections, and then we estimate the housing need via planning indicators. Now, when we calculate housing need, we can match housing need to housing capacity based on urban planning designs. And then we can propose housing capacity that is able to meet future housing needs. So when we get like this lower tier scenarios from the AI, we can evaluate them, we can see them and evaluate them and change them, propose new housing capacity, then match this housing capacity to floor space that we've developed, and therefore be able to calculate new proposed population, which can feed in as a new scenario in Quant. And this creates a feedback loop from a lower tier to an upper tier model. And this diagram shows exactly how this is done. We have a city model on one hand side, on the right hand side, and a regional model on the left hand side. And what we do is we take calculated provisions, whether that's housing service provision, employment service provision, or education service provision, and we distribute it based on planning regulations and indicators to the according land uses, whether that's schools or houses or employment areas. And by adjusting the different let's say urban planning scenarios, we can redistribute these provisions. And here we see such an example in the Queen Elizabeth Park, where there's the new UCL campus programmed and a new houses programmed. And we can see how using Quant, we can predict whether there's going to be an excess of housing supply, or if there's going to be a shortage of housing supply in this case, through the railway infrastructure, we see that there's a more need for housing in this red volumes that they're developed here. I'm going to be very quick because I'm aware of the time. I'm just going to show this video which explains it all, how Quant is linked to a 3D interface that we can use sliders to change population on a lower tier, such as very simple, or change uses such as retail, and create employment. So imagine this in a big table, which is still locked up. By changing this land uses and populations and creating employment or changing employment, we can create new lower scale scenarios. We can evaluate the AI, and then we can feed it back to Quant and see the effects of these changes on a lower tier planning model. So this is where speed is very important, as Richard mentioned, because when you click this button, you really want to see these results straightforward coming to your browser. So yes, I'll leave Richard with the conclusions.
Okay, I think we're running out of time, so I'm just going to say this just rounds up all the 3 different approaches that we use, and then I'm going to hand over to Will and the next panelist.